Hi, my name is Cooper Parton, and I'm a developer on the Direct Storage for Windows team. And I'm happy to be here to talk to you about our recently released Direct Storage runtime. I'll start by giving you an overview of some of the challenges that games encounter today and how Direct Storage can help address them, as well as a tour of the runtime, some of its inner workings, touching on the architecture, and I'll give you some good developer tips to help you have a successful integration into your title. And I'll follow up with pointers to documentation, samples, and tools. And of course, at the end, I'll give you a peek at our roadmap to tell you what's next. So storage hardware is getting faster, and the existing APIs used to access that I/O on that hardware, they haven't changed, and they just can't keep up. CPU speeds are really not growing that fast as the storage hardware speeds. Now, NVMe SSDs, well, they're becoming the standard in the gaming industry today, and they currently ship on the latest generation of consoles. Now, meanwhile, games are getting larger, they're getting more expansive, and assets for those games are becoming higher fidelity, and as a result, they're growing in size. Now, this puts a lot more pressure on the I/O bandwidth, to load, decompress, and rehydrate these assets. Now, texture and geometry streaming technologies are some of the reasons that we are seeing this increased demand. There's a decrease in the size of the I/O that is being issued and an increase in the number of I/O operations. So how can we address this? Direct Storage on Windows. So the Direct Storage runtime, it provides game developers the ability to reduce that CPU usage as well as the load times in their title. And now this tech will work well with NVMe drives in combination with, streaming architectures. Now, reducing the CPU overhead. Well, this is a key benefit that I really want to stress, and you're going to hear me say it multiple times in this talk. The more CPU cycles that are freed up for a title, they can be leveraged elsewhere in that title. Improved background processing, AI workloads, or anything, additional experiences, for example. Now, the runtime also supports ways for a title to use their existing CPU-based decompression. Now, titles do ship with decompression today, so we know the subsystems exist, and this runtime will allow you to use those. But I'm going to talk a bit more in a bit about how we plug in that architecture. Now, Direct Storage, it's been around for a few years, and it was actually originally developed for the Xbox Series X and Series S consoles. There are console titles today, AAA titles that use Direct Storage for their loading. Now, Direct Storage on Windows is not a direct port of the Xbox implementation. This is a new implementation, and we tailored it to get the most out of that PC platform. Now, I've told you what Direct Storage is. Let's talk about that CPU reduction that I referred to there. So Direct Storage is designed for modern gaming systems. Now, it handles smaller reads really efficiently, and you can batch things together to get more work done. When fully integrated with your title, Direct Storage with an NVMe SSD on Windows 11 reduces the CPU overhead in a game 20 to 40%. Now, this is attributed to the advancements made in the file I/O stack on Windows 11 and the improvements on that platform in general. Now, using those CPU savings to push even more I/O operations, like the streaming technology I mentioned earlier, through that file stack, they will yield better performance. This will enable your title to actually start hitting those I/O bandwidths of those faster drives. Now, the Win32 APIs that exist today are very CPU intensive. They have an upper bound on how much you can actually push through them with heavy workloads. So the more I/O you push through the APIs, the higher that CPU cost will be. Now, I'm not saying that the Win32 APIs are bad. It just means that they were designed to be a more general purpose file I/O API. And Direct Storage is really focusing on game loading scenarios and high performance. So if I integrate Direct Storage into my game, where will it be able to run? Well, Direct Storage works on Windows 11 and is compatible on Windows 10. Now, Windows 11 comes with that updated file I/O stack I mentioned and NVMe drivers that will result in I/O performance gains and reduced CPU usage. There it is again, CPU usage. For optimal benefit, having an NVMe SSD with a min speed of 2.5 gigabytes per second or higher is actually recommended and puts you into that optimized bracket. On Windows 10, Direct Storage will fall back to use an optimized file I/O layer that we built on top of the Win32 APIs. This fallback layer really leverages good patterns like async I/O and completion ports, And it's going to work very hard to give you the most performance you can get in throughput on Windows 10. So you will also need a DirectX-capable GPU, one that supports shader model 6.0 or greater. And the Direct Storage primary goal, now this is going to sound like an advertisement, but it's true. Its primary goal is to choose the best, most performant way to achieve your loading demands based on the platform you're running on. Now, titles do not need to be concerned on whether they're running on Windows 10 or Windows 11. They just work to the API, and we do the rest. Now, let's dig a little bit more into this technical detail here. So Direct Storage provides a queue-based programming model. Now, this enables you to submit work in batches and monitor those batches as they get processed by the runtime. Now, the queue behaves more like a D3D12 command queue, if you're familiar with that. Now, the unit of work that's submitted to this queue, it's called a request. And you'll hear me say request quite a bit from now on. The request defines a source, which is a file, an offset, and a size, or it could be CPU memory, and a destination, which is commonly a D3D12 GPU resource. Now, a destination could also be a memory pointer if you desire. Supported GPU resources, the destinations, will include things like textures with full MIP chains, texture regions, tiles, individual sub-resources in a texture. So Direct Storage under the covers uses the D3D12 runtime to ensure that that source data that we just read from the file is properly copied to the GPU memory in the correct swizzled format for whatever GPU you are targeting. So this is a picture of the high level of what's going on a single request. And this example here works with uncompressed data, and it's considered to be a fast path, mainly due to the minimal amount of processing required when the data comes off the disk and gets copied to the GPU. So the data is read from a source, that's that purple box there, from a file, that's a source is a file in this case, into a staging buffer, which is required by the D3D12 API. So we are talking about a GPU resource destination here. And then it follows completely through, so it lands onto the GPU. Again, this is a fast path, uncompressed data. So what about compressed data? Titles today use compressed data. Well, compressed data looks very much like the uncompressed workflow. And the runtime will take a small detour to include the title in the decompression process here, but the rest of it is the same. The data is read from a source, from the SSD again, into the CPU staging buffer, which will be handed off to the title for decompression. Now, in my next slide, I'm doing a little teaser here, I'll tell you how that handshake works and what's involved. But one thing I do want to point out, and it's super important for me to note here, is that Direct Storage does not come with any built-in CPU decompression formats. It doesn't understand the type of data. It's your title that will choose how to decompress this content. And it will work with your title to make sure that this can happen in a very timely manner. Here's an example of CPU decompression. Now, I want to point out that we will have a sample on our GitHub repository that will help demonstrate this in more detail, and I encourage you to check that out. It's a pretty cool sample. Now, when compression type is set to custom, the Direct Storage runtime will put those requests through what we call a custom CPU decompression queue. And this is something that will allow us to integrate with your job system and your decompression tech that exists today in your title. Now, you'll get all the benefits of the fast I/O, and then you control how quickly you can decompress, and Direct Storage will take the rest and coordinate all of this for you. Now, the custom CPU decompression queue, it's different than the runtime queue that I was referring to that takes requests. This is an interactive component, and it's used by the runtime and the title together to manage these workloads as CPU decompression gets to be required. The title pulls these items off the queue, decompresses the content using whatever mechanism you want, and then notifies Direct Storage when it's done. The Direct Storage runtime then picks up the uncompressed data and, just like the slide before, continues it through. So now let's talk about multiple requests. So to maximize your I/O throughput in Direct Storage, you're encouraged to batch many requests together. Now, batches of work added to the queue, they can be monitored by your title by using either an event-based model, that's D3D12 fences, which you can pass a handle and wait on them to be signaled, or even a polled model, leveraging the new Direct Storage status arrays. It's whatever you see fit in your title to use. So let's look at a queue with a bunch of batches in it. So this diagram shows the direct storage queue. It has a whole lot of batches in it, and queues are defined with a capacity that your title controls. So the top line of this diagram is a deep queue, and I zoomed in a portion of it to show these individual requests. The orange blocks, those are the requests. The blue blocks are signals for the monitoring batches. Again, you have your event-driven or your polling based. And the green blocks are points where the queue is told to submit the data. So the labels I put on this diagram are actually the method names on the direct storage queue interface. And I did this to sort of tie the API to this diagram and help drive the concepts home here. So in queue request, well, that's used to put work into the queue for execution. Now requests, again, we define them as having a source and a destination. In queue signal, well, this is where you insert your chosen monitoring mechanism, polling or event-based. And submit, well, that kicks the work off. Now, one thing I want to also add is that the queue will automatically submit on your behalf if the capacity reaches a certain threshold. Now, this is mainly done to keep the work flowing through the system. We want to make sure that that work is always going and that the queues are not blocked up. Now, the batches themselves, they will always complete in order. But the individual requests, those are the ones that are file I/O reads. They can complete in any order, and that's purely based on how the I/O in the file system decides to schedule it. So one thing you can guarantee on is that the monitoring mechanism, when signaled, that you are guaranteed that your entire batch is complete. Now, you can get the most out of direct storage by doing a little bit of upfront thinking here. Like, if this is a retrofit into an existing title or a completely new title, you really need to consider your data. So first, and probably the most important, is just understanding your title's loading needs and approach. Like, are you using a streaming system? Are you following more of a bulk load scenario? What data is required? And what order, what optimal order is that data in? And I want to stress the order because that is where you're going to get your most throughput here. The direct storage runtime thrives on batched workloads. And so you can collect and submit as much as you can at once. Stalling that pipe with interdependent reads will kill your performance. So keep it fed. It will deliver the performance you need. Now, never, I'm using the word never, and it sounds very strong, but never do an easy one-to-one replacement of your Win32 I/O calls with direct storage calls. And I'm speaking about replacing read file with an in-queue request and submit pattern. See, these will not give you good performance at all. In most cases, they may give you worse performance, because even worse than your current Win32 implementation. And that's mainly due to the fact that the queue will be stalling, and the overhead of that stall is going to cost quite a bit. Okay, now you've heard all this complexity and all this new infrastructure you're putting into your title. So how do you debug this? PICs. So tooling support is super important for the DirectX family of APIs. And PICs, it's available there to help debug your title. Now, direct storage and PICs can be enabled by checking the file access I/O checkbox in the timing capture settings. Now, once that's been enabled, a timing capture taken with PICs will start showing additional lanes in the timeline. And there will be a new lane per direct storage queue created by your title. Now, you're encouraged to name your queues. You can call them anything you want. And that will make them a lot easier to identify. If you've ever looked at a timing capture in PICs, there are a lot of lanes. A tremendous amount of data is thrown at you at once. And so anything you can do to make it easy, I advise you do that. So the queue lane will show lots of information about what's happening on your queues themselves. You'll see requests that you've enqueued. You'll see signals that you've placed. And you'll actually see where the data is being submitted. Now, you'll also notice that you can get extra information about the batches that you have issued in your queue. So you can see things like the number of requests in each batch. You can see how long the batch took, and even the total number of bytes, the size of that batch, which are real important. Now, PICs also contains additional information in this timing capture, which I think is very important for you to just kind of keep in mind. You can see what all the different threads are doing in your app. You can also check out context switches to find out where time is being spent. And you can really optimize your loading code and get an entire story of what's happening just from a PICs capture. So I encourage you to download this tool and try it out. All right, you have your implementation done. it's optimized. You've debugged it, it's ready to go, and you're using direct storage. So what's next? Well, our first release introduces CPU decompression, and that's where you're using now. But we're not going to stop there. We're going to continue to free up a lot more CPU cycles by finding more creative ways to offload decompression to other parts of the system. For example, the GPU. In the future release, you'll be able to use direct storage to decompress assets using that GPU. And this is more CPU savings for you, where you can do more additional work in your title. So stay tuned to our sites and our blogs and links, and we'll give you the information when that comes online. Now, I encourage you to start integrating now. Please, get it into your titles. It'll set you up for the future. Our runtime is always looking just a bit ahead of where we are today to make sure that we can address the needs that your title is going to have in the future. If you do this, you're already set up to take advantage of these new changes. And even more so when GPU decompression comes online, that integration into your title will go super smooth. So check out the Direct Storage landing page, which has links to our great resources like our NuGet package, our samples, our docs. And I encourage you to join our Discord channel. This is a place where you can connect with other developers who are actively integrating direct storage into their titles. And we have a presence there as well, and we'll listen to your questions and get your feedback and really help those. So finally, I also encourage you to check out the GDC talk, Breaking Down the Worlds of Athea, the Technologies of Forspoken. Now, in this talk, you will hear first-hand information and experiences from a AAA developer that has integrated direct storage into their runtime today. So thank you.